Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for the introduction. Welcome to Cambridge. As you can see, it's raining outside. We spoiled you with sun for a couple of days, and now we're giving you the true Cambridge experience. I'm Hitesh Palani, and today I'll be talking about work that I've been doing with my colleagues, Paolo, Gom, Thomas, Greg, and Enino, all part of Systems and Networking Group. So, over the past couple of years, we've been looking at the systems and network aspects of building predictable data centers. And in this talk, I want to give you an overview of this work and describe a few of the systems we've designed. Now, when we started this work, the explicit project goal was to enable predictable application performance in multi-tenant data centers. Here, the term multi-tenant data center refers to any data center with multiple tenants. This includes private data centers like the Bing data center, and it also includes the public cloud like Microsoft Azure that you'll learn about later today, or Amazon EC2, where users or tenants can rent virtual machines on demand. However, before we dive into the technical details, I want to quickly go over how these data centers operate today. And of course, if at any point of time you have questions, please feel free to ask. It's always nicer to have a more discussion-oriented talk. So, today's cloud providers offer a very simple interface to their users or tenants. Tenants can ask for any number of virtual machines, and they are charged on an hourly basis. So you can go to Azure today, and hopefully you'll do that in the afternoon, and you can get small virtual machines for 8 cents an hour. Hopefully your afternoon stuff will be free. This is great. However, there's a problem here, and it's the fact that the performance of applications in these cloud environments can be very unpredictable. I'm going to use a simple example to explain what I mean by that statement. So let's imagine a user, say Ken, who does in-house data analytics. So every day, Ken runs a MapReduce job on his enterprise machines in isolation, and say the job takes 4 hours to finish. Now, Ken hears about Azure, and he takes his business to the cloud. He executes the same job on the same number of machines in an Azure data center. However, as you can see, the job completion time can be inflated, and that's not it. Because users are charged based on how long they occupy their virtual machines, poor Ken ends up paying more too. So it's a double whammy. Now, this is a contrived example, but the important point here is that today both the performance and the cost for tenants can be unpredictable, which is often cited as a key hindrance to cloud adoption. Of course, an obvious question to ask is, why is application performance so unpredictable? And to answer that, let's look at what happens inside one of these data centers. So we have Ken renting his virtual machines. He executes his MapReduce job. This job involves shuffling data between these virtual machines. So it results in network traffic. Beyond this, the job needs to read its input from the shared cloud service. So it leads to network traffic and storage traffic. And of course, there are other users in the cloud, each running its own application. The thing to note here is that the underlying network and the shared storage service are both shared resources. So the network performance and the storage performance you achieve depends on what other tenants happen to be doing. So it is these shared resources that are the root cause for unpredictable application performance in the cloud. And actually, there is plenty of evidence regarding this in the wild. Over the past few years, there have been a bunch of measurement studies by external researchers looking at various cloud providers, and they measured the network bandwidth between VMs in the same data center. And you can see, across the board, there is a lot of variability. In some cases, a factor of 5 or more. And this network performance variability has been shown to be a key contributor to application performance variability. And the same variability applies to storage performance too. Now, up until now, I've focused on the public cloud. But the same unpredictability problem shows up in private cloud scenarios too. So in this example, we are looking at a small enterprise cluster, which could be a cluster at your university. It could be a cluster at any small enterprise. On the right, we have a compute stack with a few physical servers that are hosting virtual machines. On the left, we have a few shared file servers. Now, the red virtual machines in this case happen to be running an aggressive application that generates many I/O requests per second, input-output requests per second, which in turn loads these file servers, and when blue VMs generate I/O requests, they get really poor I/O performance. Actually, if VMs get really poor I/O performance for critical paged I/Os, they can even blue screen. They'll just crash, which is obviously something that we'd like to avoid. So in both these cases, a public cloud and private cloud, we have the problem of unpredictable performance because of shared resources. And this is what motivated the Predictable Data Centers project, where, as I mentioned, the goal is to enable predictable application performance in these shared data center environments. Now, the way I like to think about this project is we are building upon a few key building blocks. Dedicated virtual machines that exist today. And what we want to do is we want the same kind of predictability to apply to shared resources like network and storage. So in our research here, we've developed these few systems that enable a predictable network and a predictable storage. In this talk, in the first part, I'm going to focus on Oktopus, which was our first project in the area, where we offer bandwidth guarantees in cloud environments. I'm going to give you a technical overview of Oktopus, and then in the second part of the talk, I'm going to briefly comment on the other systems to show you how the research has evolved and what our current direction is. So first up, we'll do Oktopus. Now, in case you were wondering where the name came from, I don't know if there are soccer fans here. It was named after Paul the Octopus, who gained a lot of media attention for being able to predict the outcome of soccer games. I see a couple of nodding faces. He passed away a couple of years ago. May his soul rest in peace. Anyway, the basic idea behind Oktopus is really simple. All we are arguing is that tenants, apart from being given virtual machines, as is the case today, they should also be offered a virtual network connecting these machines. Now, this virtual network is a private network for the tenant, and it decouples their network performance from the underlying infrastructure, thus allowing them to reason about their applications in a simple and intuitive fashion. So if you're a tenant, what this virtual network does is that it ensures that your performance does not depend on what other tenants happen to be doing. The nice thing about Oktopus is that it does not require changes to network infrastructure, and it does not require changes to tenant applications. So it's incrementally deployable, which is great from a deployment perspective. And finally, what we found was that network bandwidth guarantees are great for users because they get predictable performance. But in our research, we found that they can benefit the provider too by increasing the overall cloud throughput. So it's a nice win-win situation. And this is something that I'll show as we go along the talk. Now, once we settled on the basic idea of offering virtual networks, yeah, question?
What do you mean by cloud efficiency? What's the definition about the efficiency of cloud?
Yeah, I'll explain that in detail later, but a short answer right now is the system throughput. How many tenant jobs can the cloud provider process in any given unit of time, which in turn influences revenue. But I'll come to this in detail later. So once we settled on the basic idea of a virtual network, the question for us was, what are these virtual networks that we want to offer to users? What are the semantics of the bandwidth guarantees we want to offer? What are the virtual network abstractions we want to offer? Two main design goals influence a lot of our thinking in this direction. First, from a tenant's perspective, we want these virtual networks to be simple and intuitive. We want tenants to be able to reason about the performance of their applications when running on top of these virtual networks. Second, from a provider's perspective, we want to retain provider flexibility. We want the provider to be able to map many of these virtual networks and many tenants on their infrastructure at the same time. Now, these two are competing goals. Tenants want strong guarantees, while providers would want to offer weak guarantees so that they can achieve a lot of multiplexing. Now, in all the virtual networks we've designed, there's a common theme, and that is this notion of aggregate bandwidth guarantees, which in turn allows us to balance these two competing goals. Now, the best way to explain what I mean by an aggregate bandwidth guarantee is to look at some of the virtual networks we've designed. So let's do that. The first virtual network we designed is something called a virtual cluster. And it's motivated by how tenants run applications in enterprise settings or any private setting. These applications run on a set of physical machines that are connected by an Ethernet switch. And I'm sure you're used to such an setup at your universities when you run your experiments. And we want to replicate the same kind of setup in a cloud environment, the hope being that this will make it users to migrate to such cloud environments. So with this abstraction, a tenant's request is characterized by two parameters, N and B. What the tenant gets is a set of N virtual machines, each connected by a virtual link of capacity B to a virtual switch. So in effect, the tenant gets a private network that is very similar to the physical network they're used to in their enterprise settings. Two things I want to reiterate here. First, this is a virtual network that's separate from the underlying physical network. So if you're a tenant who's renting N virtual machines, I could place these VMs, the provider could place these VMs anywhere in the physical data center. And all we are doing is we are offering this illusion of a virtual cluster that connects your VMs. Second, with the virtual cluster abstraction, each VM gets an aggregate bandwidth guarantee for its outgoing and its incoming traffic. So if you have a scenario like this where VM1 is generating a bunch of flows, what our abstraction says, or what we are promising, is that the aggregate rate for these flows should be limited to B Mbps. Similarly, if the VM is receiving a bunch of incoming flows, again, the combined rate for these flows should be limited to B Mbps. That's what our abstraction is promising. So that's an example of an aggregate guarantee. Taking a step back, the way the system works is when a user comes in, he specifies the number of virtual machines he needs and the virtual network he requires. To offer this illusion of a virtual network, Oktopus relies on two main components. First, there is an admission control and a VM placement component that carefully places a tenant's VMs such that their bandwidth guarantees can be met. Of course, if the guarantees cannot be met, the tenant request is rejected. Once a tenant request has been accepted and its VMs have been placed, we then need to enforce these bandwidth guarantees. We need to make sure that each VM gets the guarantee it has been promised, no more, no less. So over the next few slides, I'm going to comment briefly on these two components to give you a feel for how Oktopus works. First up is VM placement. And I'm going to use a simple example to give you the intuition behind our placement algorithm. So we have a toy data center with 4 physical machines or 4 physical servers, each with 2 VM slots. Also, let's imagine a tenant who's requesting 3 virtual machines that are connected by a virtual cluster, as shown on the top right-hand corner of the slide. Now, here I've shown a placement of these VMs, and I've highlighted the physical network links that connect these VMs. Now, it is these highlighted links that may carry the tenant's traffic. And so, it is on these highlighted links we need to ensure there is sufficient capacity to satisfy the tenant's bandwidth guarantee. Here, I've shown an alternate placement of these 3 VMs, whereby we pack the VMs closely. And you can see this reduces the number of physical network links that have to carry the tenant's traffic. And so we have to reserve bandwidth for the tenant on a fewer number of links. So from the provider's perspective, this nice compact placement is preferable to the one that I'd shown earlier. And the big question for us was, how do we find such nice compact placements? As part of Oktopus, we've designed a VM placement algorithm that achieves two things. First, it achieves correctness. That is, if a tenant's VMs are placed and he's admitted, their bandwidth guarantees can and will be met. Second, it strives for efficiency. That is, it tries to find these nice compact placements that minimize the impact of the tenant on the underlying infrastructure, thus allowing the provider to pack many tenants on the data center. Now, I'm going to skip the details of the placement algorithm. For those of you who are interested, it's a greedy first fit placement heuristic that was inspired by heuristics used in multidimensional bin packing. If you're interested or if you work in the area, please come talk to me and I'll be happy to show you the details over a whiteboard or take a look at our paper. Now, once a tenant request has been accepted and its VMs have been placed, we then need to enforce their bandwidth guarantees. And again, I'm going to use an example to give you a feel for how this works. There's a tenant who's renting n virtual machines. He's been promised a virtual cluster. And remember, this is just an illusion we are offering. Now, this virtual cluster promises that each VM gets an aggregate guarantee for its outgoing and its incoming traffic. So if you have a scenario like this, where VM1 is generating a bunch of flows, the combined rate for these flows should be limited to this value B. This is easy enough to achieve simply by putting a rate limiter at VM1, a simple software component. Now, the virtual cluster abstraction also promises that the combined rate for incoming flows should also be limited to B Mbps. So if you have a scenario like this where VM1 is now receiving a bunch of incoming flows, again, the combined rate for these flows should be limited to B Mbps. This is a little bit harder to enforce because we now need to control the aggregate sending rate of a set of VMs. Actually, taking a step back, since all our virtual network abstractions have this notion of aggregate guarantees, in order to enforce them, we need to control the sending rate of a distributed set of VMs, which is precisely the distributed rate limiting problem. So with distributed rate limiting, or DRL, we have a set of distributed entities, and the goal is to control their aggregate sending rate. In our case, a distributed set of virtual machines. So what we realized was, in order to enforce our abstractions, we need to solve this DRL problem. Now let's look at a quick example. We have n virtual machines and we want to control their aggregate rate to some value B. The naive solution here would be to do static partitioning. Each VM gets an equal share, which in this case would be B divided by n. However, as you can imagine, that's strictly suboptimal, because if some VMs are not generating traffic and not using up their quota, other VMs are not allowed to pick up the slack. So what we really want is a work conserving solution whereby VMs with traffic to send are allowed to send it as long as the aggregate rate limit is not exceeded. And this is precisely what our DRL solution tries to achieve. So to give you a sense of how it works, let's go through a simple example. Again, a toy data center with a few physical servers and a physical network. There are two tenants or two users here, a blue tenant, a red tenant. The blue tenant has been promised a virtual cluster with some aggregate guarantee for each VM. Now, as I mentioned, to enforce this abstraction, we need to do DRL. And to achieve this, we associate a controller with each tenant. Here, I'm showing the blue controller, which is responsible for the blue VMs. And periodically, this controller gets information regarding the traffic statistics of individual VMs. Based on this information, the controller uses the algorithm to determine the per VM rate allocation such that the aggregate rate limit is not exceeded. This per VM rate allocation is then communicated to the individual physical servers where it is actually enforced. In our prototype, this is done inside Hyper-V, inside the virtualization layer, and that has two implications. First, we don't need to trust the tenant applications, or we don't have any trust issues because tenant applications cannot muck with our per VM rate allocation. And second, we don't need to modify the guest OS, nor do we need to modify the tenant application, which is great from a deployment perspective. So that's how DRL works in our framework. Now, as I mentioned, we came upon the DRL problem because we were trying to enforce our virtual network abstractions. But broadly speaking, DRL can be seen as a building block that can be used to enable novel scenarios that require predictable performance. For example, I showed you how to do DRL for network, but you can apply the same concept to other shared resources. For example, in follow-on work, we have done DRL for storage, and that's something that I'll be talking about later in the talk. So the point here is that DRL is this key technology that allowed us to enable predictable network and predictable storage, on top of which we plan to do predictable data centers. So let's see how this works in practice. We built this, we deployed this on a small test bed upstairs on the 3rd floor. Actually, the test bed is on the 5th floor, but if some of you are interested, I can show you a demo later. We also used a simulator to see how Oktopus would work at data center scales. And the key message what we found was that guaranteed network performance is great for users because they get predictability, but surprisingly, it's great for providers too because it leads to increased system throughput or cloud efficiency. So the use of virtual networks benefits both tenants and providers, and this is something that shows up in our results too. So just a quick experiment. What was happening in this experiment is tenants were coming in. Each tenant was requesting some VMs and a virtual network. On the x-axis, we have the target data center utilization, or how loaded the data center is. So as tenants arrive faster, the utilization increases. On the y-axis is the percentage of tenant requests the provider had to reject. So lower is better. Now, I want you to focus on two lines. The red line, which is baseline, and it represents the operation of today's data centers, where users don't get any bandwidth guarantees, and the green line, which is the virtual cluster abstraction. The other two lines, please disregard. They are other abstractions that I haven't described in this talk. Now, you can see almost across the board, virtual cluster allows the provider to accept more tenant requests as compared to baseline. To put this in perspective, most data center operators target a utilization of around 70 to 80%. And at 70%, we find that with the virtual cluster abstraction, the provider is able to accept 16% more requests as compared to baseline. Now, that's a counterintuitive result because with baseline, there are no guarantees, whereas with a virtual cluster, a tenant request is only accepted if we can satisfy their bandwidth guarantees. So what's happening here is that with baseline, tenants don't get guarantees. Some of them get really poor network performance. They become outliers, which drags down the system throughput. As a contrast, with Oktopus, tenants get guaranteed bandwidth. There are no outliers, and so we don't have that problem. And this shows up, or this has implications for cloud pricing too. So we used today's Azure pricing data, and we did a simple cost analysis. And just as a simple sample point, at a load of around 75%, we found that the median tenant costs with Oktopus reduced by 42%, while the provider revenue increases by 20%. And again, that's a counterintuitive result, but it comes from the fact that Oktopus increases system throughput, more tenants pass through the system, so individual tenants can pay less while the provider revenue increases. So this is the nice win-win situation that I was talking about, which is great because both tenants and providers are happy. So that's the Oktopus part of the talk. Now, When we did this work and I went out and gave talks, we got lots of useful feedback from our product groups in Microsoft, from our colleagues in MSR, from the broader research community. And that has influenced some of the follow-on work that we've done. Actually, we pursued 3 main research directions, which you can see were greatly influenced by 3 questions we were often asked. And I want to comment on each of these briefly. The first question we were often asked is, network bandwidth guarantees are great, but can users actually specify their network requirements? Very few users are sophisticated enough to say, I want 10 virtual machines with 500 megs of network bandwidth. And that's a fair comment. So this motivated us to design Bazaar, a system that enables a higher level interface between tenants and providers in these cloud environments. With Bazaar, tenants only specify high-level goals regarding their applications. These could be performance goals. I want my job finished in 3 hours, or cost goals. I have a maximum budget of $300. And these high-level goals are automatically translated onto the underlying resource requirements. For example, to finish a job in 3 hours, you need 25 virtual machines with 500 megs of network bandwidth between them. Now, I think this is pretty cool, but to achieve this vision, we had to solve 2 key challenges. The first challenge was performance prediction. Given a job and given some set of resources, we need to be able to predict how long the job would take to complete. Now, performance prediction is a very hard problem. There is tons of existing work. And actually, for arbitrary applications, I'd like to claim it's almost an intractable problem. So we focused on a specific yet important class of cloud applications, data analytics. And we built a performance prediction tool for MapReduce jobs. The way this tool works is, given your MapReduce job and some sample input data, we are actually going to execute and benchmark the job. We're going to collect some statistics, which is then used to predict the performance of the job if it were running on the actual input on some number of resources. The second challenge we had to solve was, there may be more than one way of satisfying a given high-level goal. For example, if I had to finish your job in 3 hours, we could use 25 virtual machines with 500 megs of network bandwidth, or we could use more VMs and less network bandwidth. Trade off one resource for the other. Now, from a tenant's perspective, as long as the high-level performance goal is met, it does not matter which resource combination we use. But this flexibility of the resource combination is important from the provider's perspective. So we devised a resource selection heuristic that chooses the best resource combination from the provider's perspective, which in turn would allow the provider to accept more future tenant requests. The really neat thing about Bazaar is its implications for cloud pricing. Today, cloud providers do resource-based pricing, right? You go to Azure, you pay some cents per hour for each VM. With Bazaar, we can enable job-centric pricing. So we can move away from resource-centric pricing. The provider can say things like, to finish this job in 3 hours will cost $300. Actually, the provider can go even further, and he can offer multiple cost performance options to the users, which is great because users get predictable performance and predictable cost. So we built the Bazaar system, and just to give you a sense of how it performs, the graph is similar to what I'd shown earlier. X-axis is the target occupancy, or how loaded the data center is. Y-axis is the system throughput or system good put with Bazaar as compared to baseline. And again, at a load of 75%, we find that Bazaar improves the overall system throughput by around 56%, which is great because tenants, their jobs finish on time, their performance goals are met, while the provider has increased system throughput because of the extra flexibility, which hopefully would lead to higher revenue. So that's Bazaar. Now, the next question we were often asked is, network bandwidth guarantees are great, but what about statistical multiplexing? With Oktopus, users get bandwidth guarantees, but they are not allowed to exceed their guarantee even if there is unused network capacity, which is a little bit funny. So this caused us to revisit our network sharing requirements. To address the multiplexing question, what we want to do is offer minimum bandwidth guarantees that tenants can exceed if there is unused network capacity. And this is great because tenants get predictable performance while the underlying network is efficiently utilized. Another requirement here is payment proportionality. So the guarantees that I'm going to give you as a tenant should be in proportion to your payment. Now let's quickly look at how existing solutions fare with regards to these three requirements. So in today's data centers, you can use the transport protocol of your choice. You can use TCP, you can use UDP, you can use any transport protocol. And what most of these ensure is high utilization of the network, but users don't get bandwidth guarantees and there is no notion of proportionality. So this has prompted a lot of work in this area. As I mentioned, with Oktopus, we offer bandwidth guarantees that you cannot exceed even if there is unused capacity. Now, I'm not going to go into the details of all these solutions, but the key point here is that none of these satisfy all three network sharing requirements, and all of these focus on traffic between VMs of the same tenant or intra-tenant traffic. Actually, we've done measurement in about 8 Azure data centers, and what we found was that a significant fraction of the cloud traffic is actually between tenants. So this motivated us to design Hadrian, a network sharing framework that caters to both inter and intra-tenant traffic, and it satisfies all three network sharing requirements. Now, just like Oktopus, Hadrian comprises of three components. There is virtual network abstractions, there is a placement algorithm, and a bandwidth allocation strategy. And all these are more sophisticated than Oktopus because of the more advanced network sharing requirements. For example, the bandwidth allocation strategy in Hadrian is weighted sharing of the network as compared to reservations in the case of Oktopus. And what this allows us to do is offer minimum bandwidth guarantees to users that they can exceed if there is unused network capacity. And again, just to give you a sense of how it performs, similar sort of a graph comparing the baseline scenario against Oktopus, against Hadrian, and by utilizing the network more efficiently, Hadrian is able to accept more requests than baseline and as compared to Oktopus. So that's the statistical multiplexing question. Now, the final question we were often asked is, what about other shared resources? When you run a MapReduce job in a cloud, it leads to network traffic, but it also leads to access of the shared cloud storage servers. And it's this question that motivated the design of Splitter, which is the predictable storage component of the PDC framework. Splitter allows the cloud provider to express high-level performance policies regarding storage flows from VMs to storage servers. Now, the structure of these policies is shown here in red. For all I/O traffic, input-output traffic, from a set of VMs to a set of storage servers, we can specify a service level agreement or an SLA. This SLA could be a bandwidth guarantee, it could be a minimum bandwidth guarantee, or it could be a priority level, which I think of as poor man's latency control. Now, the thing to note here is that Splitter allows both point-to-point guarantees, that is from a single VM to a single storage server, and it allows for multi-point guarantees from a set of VMs to a set of storage servers, which is again an example of our aggregate guarantee. Just a quick view of the architecture. This is a block diagram, don't get scared, I'll explain this. This is a block diagram of how IOs flow from an application inside a VM to the actual disk. So when you do a file read or write, what happens is you're going through the file system and the block device inside your guest operating system, and so on and so forth till you get to the actual disk. Now, Splitter comprises of two main components. First, we've added queuing functionality at various stages along the I/O path. And what this allows us to do is it allows us to direct I/O packets to different queues and thus treat them differently or offer performance differentiation. The second component is a controller, just like in the case of Oktopus, that interacts with these stages, and this controller translates high-level performance policies into configuration of these individual stages. So this configuration includes how packets should be queued, as in given a packet, which queue should it go to, and what are the performance properties associated with these queues. Now, as you can see, this design is very similar to Oktopus, and the challenge in Splitter was to account for storage idiosyncrasies. For example, if you think about rate limiting, which is typically done in token buckets, I don't know, the network crowd probably understand that. We've known that in the network community for years, if not decades. However, rate limiting for storage is particularly problematic because the capacity of the underlying resource varies depending on the workload, which is not the case in a network. In a network, a 10 gig link always behaves like a 10 gig link. In the case of storage, if you get a disk mark at 10 gigabytes per second, the actual throughput you're going to get depends significantly on the workload that you're offering. So that's an example of a challenge that we had to solve in the Splitter framework. And this is some ongoing work where we are collaborating with the Windows File Server team to enable storage SLAs in the Windows Server framework. So that's the last question. And I don't know how we're doing on time. I did not. Oh, we have plenty of time. So, well, I'm going to finish here, but I have tons of backup slides. So if people have questions, we can do questions, or we can go into various details. So we started with Oktopus, which is the predictable network part of the PDC framework. With Oktopus, tenants get a virtual network that is similar to the physical network they are used to in enterprise settings. And what we found was that this can benefit both tenants and providers. Over the course of research, we've designed a few systems that go beyond Oktopus, and they enable predictable network, predictable storage, and they offer different kinds of SLAs. And in ongoing work, we are trying to put this all together and offer end-to-end service level agreements. So scenarios where you have network and you have storage, and you want to offer a guarantee when these resources are combined. Now, I realize there were lots of details, but the one bit of information that I hope you take away is that in our research, we've enabled higher level interfaces between tenants and providers. And what we found is that they can lead to a symbiotic relationship between tenants and providers because both parties benefit. And this is something that I genuinely believe can spur the adoption of these systems and these interfaces. So on that note, thank you all for your patience. Thanks for your time. And we can do questions if people want more details. I'm sure I have some slides, or I'm sure there are markers here. So thank you.